Why is oxygen a gas at room temperature, while iron is solid? And why does copper conduct electricity, whereas plastic doesn't? And why is silicon used in computer chips? We're going to answer all these questions and more in this video. So where do we begin? Well, our strategy is going to start by understanding the electron arrangement in the atoms that make up these materials. Why? Because by understanding how these electrons are shared or transferred between the different atoms, we can determine the type of bonding that exists. And once you understand that, we can use that to, predict what the physical and chemical properties would be, and that will help us answer some of these questions. So let's do that. Let's start with the nonmetals. You probably remember the nonmetals are on the right side of the periodic table. They are colored in blue over here. This means that they need only a few electrons to complete their octet and become stable. For example, if you take chlorine, there are 7 electrons in its valence shell, which means if it gains one more electron to become a chlorine ion, then the number of valence electrons goes from 7 to 8, giving it a stable octet configuration. This means nonmetals tend to gain electrons when they react, and in doing so, they tend to become anions. But what happens when they're reacting with similar atoms? For example, when chlorine is reacting with another chlorine atom, or for example, when oxygen is reacting with another oxygen atom. They both need electrons. So what do? Well, this time, they're gonna share their electrons. For example, oxygen has 6 electrons in its valency shell. They need 2 to complete the octet. So both the oxygen atoms will share 2 electrons each. And look, as a result, both oxygen atoms will end up with 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons completing their octet. This type of bonding is what we call a covalent bond. As a result, these shared electrons are tightly bound and not easily lost like in the case of metals. Remember, in metals, the outer electrons can be easily lost? Well, not over here. Because these electrons are tightly bound, they are localized electrons, which means they are not free to move. So, what do you think happens to their electrical and heat conductivity? Well, if electrons can't move freely, they can't conduct heat or electricity all that well, right? That's why nonmetals tend to be poor conductors of heat and electricity, which is why many nonmetal materials are used as insulators, like in the plastic sockets, or used as rubber handles, or wooden ladle, or even in insulated bottles. Okay, but can we predict their melting points? Yeah, we know that nonmetals tend to form individual molecules, like the hydrogen atoms form H2 molecules, oxygen atoms form O2 molecules, and the attraction between the atoms is very strong, covalent bonds. But what about the attraction between different molecules themselves? These are much weaker. So the force of attraction between molecules is much weaker than the force of attraction between the atoms themselves. Therefore, it takes a little bit of energy to separate these molecules, which means we would expect these nonmetals to have very low melting and boiling points. That's why a lot of these are gases at room temperature, like hydrogen, oxygen, nitrogen, fluorine. They're all gases at room temperature. And this also explains why substances like plastics can melt very easily. But what if you try to bend a solid nonmetal, like for example, the graphite in your pencil lead? What would happen then? Well, remember that covalent bonds are directional and fixed in place. If you could peek inside the graphite, you would see layers of carbon atoms that are covalently bonded. And the attraction between the layers is again pretty weak. That's the reason why you can actually write with a pencil, because when you put a little bit of force due to friction, the layer will just slide off. However, if you push in some different direction, then the bonds can easily break. And that's why your pencil lead can easily break. That's why most nonmetals tend to be brittle. So they're not malleable. You can't hammer them into thin sheets, or you can't draw them into thin wires. That's why you don't have nonmetal wires usually. And what about their shine? With no sea of free electrons to reflect light strongly, many nonmetals are pretty dull. Okay, so this was their physical properties. But what about their chemical properties? Can we predict some of them? Yeah. Remember that nonmetals tend to usually gain electrons to form anions, or they also share electrons to form covalent bonds, right? Since this is the opposite of what metals do, their reactivity pattern also often goes the other way compared to the metals. For example, in many nonmetal groups, what do you expect to happen to reactivity as you go up? Well, remember, as you go up, atoms tend to get smaller, and smaller atoms have electrons closer to the nucleus and can pull the electrons in more strongly. So the reactivity increases because remember, nonmetals want to gain electrons. So the more easily they can do this, the more reactive they are. This is why we'd expect fluoride to be more reactive than chlorine, which would be more reactive than bromine, which would be more reactive than iodine. Okay, another question we could ask is what happens when a nonmetal reacts with a metal? Well, we already know metals tend to lose electrons, nonmetals tend to gain electrons. So, if a metal and a nonmetal were to come close to each other with a little bit of energy, the electron lost by the metal can be gained by the nonmetal. So, the metal would become a positive cation, the nonmetal would become a negative anion, and as a result of the electrostatic attraction, they can stick to each other. They can form a bond. We call this ionic bond. So metals and nonmetals usually tend to form ionic bonds. And because this force of attraction is pretty strong, ionic substances often form hard crystals. They have very high melting points and can dissolve in water. And when they dissolve in water, you'll have a lot of ions, charges that can move around, which means they will conduct electricity when melted or dissolved. Finally, remember how nonmetals can form covalent bonds by sharing electrons? Well, when these bonds are rearranged or broken down during a chemical reaction, energy can be released or absorbed. For example, consider fuels like propane or gasoline. These fuels contain a lot of CH bonds, and during combustion, the bonds rearrange into new products, and that chemical change releases a lot of energy, which can be used to power our homes, for example. And because combustion reactions tend to release a lot of energy, fuels have high energy density, meaning a lot of energy can be stored in a small amount of fuel. That is just awesome for us. Okay, so we know metals have electrons that can freely move, and nonmetals have electrons that are localized in bonds. So what about elements that are in between? What about the metalloids? Well, these elements like boron, silicon, germanium, arsenic, antimony, and tellurium, we would expect their properties to be somewhat in between, which means we'd expect them to have electrons that are not as free as metals, but also not as bound as the nonmetals. They would be in between. And that in between thing actually shows up in their properties as well. For example, metalloids are solids at room temperatures, pretty much like metals. But they're also brittle like nonmetals. But some of them can be very shiny like metals. So you see, their properties are in between that of metals and nonmetals. And what about their electrical conductivity? That's also in between that of metals and nonmetals. So unlike metals, they're not great conductors, but unlike nonmetals, they're also not poor conductors. They're in between, and that's why they are semiconductors. In low energy state, their electrons are mostly stuck in place, acting like an insulator, but add a little bit of energy by adding heat or light or an electric field for that matter. And some of these electrons can break free and move so they can conduct, which means we can use this to control their conducting properties, which is pretty awesome. And that's why silicon and germanium are used in computer chips. They're used in solar panels and even touchscreens for that matter. And there's more. Metalloids often tend to form covalent bonds with nonmetals, especially in large network structures. So think about silicon and oxygen in silicates. That kind of bonding is behind materials like glass or ceramics and even cement. And silicon can also form long, flexible covalent structures called silicones. They are useful when you want something heat resistant or water repellent and stable, like medical tubing. These would be useful in cookware components or waterproof coating. And what's even more awesome is that metalloids can be added to metals to form alloys. It can change its strength and conductivity. Like, for example, by adding small amounts of silicon in aluminum, or by adding small amounts of silicon or boron in steel, we can make those materials much stronger. So, long story short, we know that metals tend to usually lose electrons, and as a result, they tend to form a metallic bond, where positive metal ions are packed together in a sea of delocalized electrons. And this model explains a lot of their physical and chemical properties. On the right, we have the nonmetals. Over here, the electrons are tightly held and they are shared in localized bonds, covalent bonding. And this explains a lot of their typical behavior, like why they act to be insulators, why they are dull, and why they tend to be brittle. And in between, you have the metalloids, whose properties are in between that of metals and nonmetals, which allows them to have this unique semiconducting properties which we use in all our chips and solar panels and touchscreens and so many other electronics. But what's really mind-blowing for me is that we were able to figure all of this out by looking at their electron arrangements, how they are shared and how they form bonds reveals deeply about their physical and chemical behaviors. That's pretty awesome if you ask me.